My name is Nishaanth Balashanmugam. I'm the CEO and Director at GH2 India. We are an industry association think tank. We work very closely with some of the large developers in helping enable the projects, policy, advocacy, etc. So we have a lot of technical, members here on this panel, and we're going to start with each of them presenting on some of their submissions for this event. Keep all your questions at the very end. So we'll get through all of these presentations seamlessly, and we'll open the floor for any questions. So with that, can I first welcome Mr. Anshul Gupta, who's the Senior Manager at BPCL. A round of applause for Anshul, please.
Yeah, thank you, Nishanji. Namaskar and a warm good morning to one and all. At BPCL Bina, we have recently commissioned a 5 megawatt alkaline electrolyzer based green hydrogen plant. So I will be sharing my experience in the execution, commissioning and operation of this plant. So to set the context, let us first see what is the use of hydrogen in refinery. Hydrogen acts as a bloodline for us. It purifies the impurities from crude in our hydrotreating unit and helps us to produce cleaner fuels. It is also used in hydroprocessing process where the heavier oils are reduced to lighter oils like diesel as a product. If you see the current refining capacity of India, it stands at 258 mmtpa and is projected to leap up to 450 mmtpa by 2035. For refiners, the hydrogen is about production requirement is about 1% of the total number, and the emissions are the major factor in our conventional SMR based hydrogen production. The emissions are almost 10x of the hydrogen requirement, and the hydrogen emissions also contribute to about 25 to 30% depending upon the refinery configuration of the net emissions of these refineries. Well, the key salient features of our 5 megawatt hydrogen plant are there are two electrolyzers of 500 nm³ each. The plant is commissioned in a 15 months time period with a project cost of 43. And let me tell you, this is one of the most energy efficient plant currently operational in India. It is the fastest executed plant in India. And capex and the capacities are also, the capex is the lowest and the capacity is the highest operational in the refineries. This is a short video of our plant. Gives a glimpses of our plant.
At the Bina refinery, with a capacity of 2.15 tons per day, this facility marks the beginning of our green hydrogen journey, driving India's shift to sustainable energy. It all started with infrastructure, the control room, switchgear room, and electrolyzer shed, each built with precision to ensure safety, automation, and operational excellence. At the core lies the electrolyzer system, where renewable electricity splits water into hydrogen and oxygen. The switchgear room manages and protects electrical loads, acting as the nerve center. Meanwhile, the control room, powered by PLC-based SCADA systems, ensures smooth and safe operations. From construction to commissioning, every step reflects our commitment to sustainability. Now, clean hydrogen flows, ready to blend with our existing hydrogen generation unit, reducing emissions and shaping a greener Bharat. This is more than a plant. It's BPCL's pledge to a future powered by green energy.
Let me come to the process description of green hydrogen. So in green hydrogen plant, there are basically three major sections. One is the electrolysis section. The other one is the gas light treatment section, and the third one is the purification section. In the electrolyze, there are two electrolyzers of 500 nm³, and KOH acts as a 30% KOH concentration solution, acts as the electrolyte, and is powered by two rectifiers of 2.5 megawatt each. Hydrogen is produced at the cathode and oxygen is produced at the anode. Then these oxygen and hydrogen goes to the gas light treatment section. There are two separators in each skid, and Then after the separation, oxygen is vented out, the lye is separated from the oxygen. In case of hydrogen, hydrogen is again goes to the purification section. In the purification section, firstly, there is a deoxo tower where is the excess oxygen in the hydrogen is removed. It is then cooled down and it goes to the drying chamber. It's an absorption based dryer. There are two dryers, one with a drying cycle of 8 hours each dryer. And then the generated hydrogen goes to our central grid of hydrogen. So this plant is about roughly 3% of our net hydrogen requirement of Bina refinery. On the quality requirements, we are producing hydrogen which is of better quality than our existing grey hydrogen unit, solely because it does not contain any hydrocarbons. And if we see the realized benefit against the target, we have achieved all our targets and we are getting a good efficiency with our plant. Let me take you the core, that is the challenges. Since was a new field for us, there were a lot of many challenges. We began this project back in 2022. So we started with tendering and vendor selection when there was no prevalent market for green hydrogen production and the vendors were also not experienced. So we developed unique qualification methodologies, evaluation methodology, so that we can provide benefit to vendors which are having good technology like alkaline, SOEC, PAM. We can give a common platform to all these technology by evaluating based on the levelized cost of hydrogen. We kept the clauses flexible. This has been a very good learning so that it gives the freedom to the vendor to design their system. We implemented, since the cost of hydrogen is green hydrogen is almost double than the cost of what we produce in conventionally. We have kept few cost control clauses in the tender, wherein we have in our conventional projects we have a redundancy in at each level that we have not considered in this project. On the statutory guidelines, back in 22, there was no any such prevalent guidelines. For us, OISD is basically the guiding authority, and OISD 241 we came at a later date. So with changing and evolving regulations and guidelines, we also did our engineering, modified our engineering. One major learning was in the engineering and supply delays. Our focus we kept majorly on the electrolyzer since it was a long lead item for us. But then these rectifier and gaslight treater skid they got delayed. Electrolyzer was on site, but due to these delays of these balance of plant equipment, we had to slightly compromise. We have to expedite our schedule on other fronts. Rectifier commissioning and stabilization is one thing wherein we have faced couple of issues. One is the frequent tripping on overcurrent that currently also we are facing, but the trippings have minimized. Earlier they used to happen on a weekly basis, but now we are seeing that has stabilized, and for past 1 or 2 months we have not had any tripping. Overheating issues is one thing because our OEM is an Indian vendor. As per their recommendation, air conditioning environment is not required for the rectifiers what they have designed. But we found it when the rectifier was commissioned and it is in an enclosed room. The heat circulation is not proper, because of which the overheating is going on in the rectifier. So later on we modified our design and put a dedicated air conditioning system over there. So one quick learning is whatever the OEM says, air conditioning system must be there for the rectifier electrical application. On the cost optimization compromises that we made, like single line instrument, single line power supply, we faced few challenges on the tripping of our single line feeders, on our single line instruments getting faulty, spurious trippings are there. Conventionally, we normally have 2 out of 3 or mid sector logic that we use normally in instrument. That was not there. But later on, we put some time delays to come out of this. In the design parameter, for some time we were not able to achieve the 100% guaranteed design. we were producing about 60 to 80% of what was the design. But with the support of our licensor and our EPC, they gave their die-hard effort, and we found out that the electrolyzer inlet temperature, the electrolyte concentration, and the electrolyte flow were the main reason why because we were getting the low hydrogen production. On the dew point side, our plant is designed for a minus 70-degree dew point, is the minimum guaranteed requirement, but we were not getting that. That also our licensor did some great work in that, and I am proud to say where other plants are struggling, they have been able to achieve the design spec. What modifications that they suggested was the put additional molecular sieve in the dryer. Uh, in the drier side, heating cycle was reduced and the temperature was increased. So these tweaks helped us to achieve the required dew point. Maintaining differential level between hydrogen and oxygen separator, it is very crucial to avoid cross contamination between hydrogen and oxygen. So those issues were there, but with we could resolve all those things. One critical issue which we were facing was the hydrogen slippage in the oxygen stream. Uh, multiple and then the hydrogen reaching close to its LEL explosive limit, lower explosive limit of 4%, due to which our plant was tripping. We found out that in the all analyzers were connected to the vent line of hydrogen stack, due to which back pressure was getting generated and our analyzer were sensing those readings. So once that we corrected that issue, the problem was resolved and we are below 1.5% now. Another thing is the increase in pH of cooling water that arose because we were using we were dosing a alkaline chemical in our cooling water circuit, which we found out at a very later stage after doing all the maintenance work on our exchanger. Then we later come out of that. That was this tiny problem which almost took us 15 days to resolve. Product sampling and testing is a challenge in current refineries because we do not have those instruments to test 5 ppm level, 5 ppm oxygen and moisture. So for that we had to rely on the analyzer. For that we ensured that the analyzers are properly calibrated, and now we have initiated the procurement of instrumentations. Those are required in our laboratory. Intermittency of RE power. Now currently this is the biggest challenge that we are facing because we have a in-house 18 megawatt solar plant. Our plant is powered by that. So we are for the commissioning part we used some grid power to commission the plant also for 72-hour trials. But now for we have to daily start up and shut down in the night because solar power is only available during the day. For that, we have a 50 megawatt upcoming wind project in Bina. So once that project is commissioned in early 27, we should be able to work the plant on 24/7 basis. The last problem that we faced was with regard to cable failure due to harmonics. This issue led to some 10 runs of cable we had to replace because there was under designing of the cable sizing was not done properly, due to which the cables were under designed, and now almost 1.5 times the cable sizing is being increased. Going ahead, what challenges we foresee in large scale as a adoption is, one is the economic gap between green and grey hydrogen price. That a gap that was earlier considered a year back, that gap was considered almost 2.5 times, but now it has come down to 1.5 to 2 times during the recent green hydrogen bids in BOO basis. Evolving technology is one thing. Alkaline, PAM, AEM, SOEC, at least there are upcoming technologies. Alkaline and PAM, though they are proven, but when these technology, we don't know currently which technology will lead the sector. So that is one thing to know before we decide to scale up the plants. Infrastructure, land requirement is almost 10x of our current green hydrogen plant. Power and water availability is one thing. Grid infrastructure for Bina refinery to have a complete green hydrogen plant, we would have to have at least 1 gigawatt to 2 gigawatt of connection from the state grid. So that grid infrastructure also needs to be strengthened. For favorable banking and transmission policy, yes, central policies have become favorable, but in states there are a lot of things which we can do to improve the transmission network and the banking policies also. Then yes, operation intermittency in RE, scalability, standardization, safety and reliability are the challenges that we foresee in the large scale adoption. Uh, well, with this, I would like to end my presentation and thank you to the IE team for providing me the opportunity to speak at this forum. Thank you very much.
Thanks, Anshul, and good job keeping to the time as well. Next, if I can have a round of applause for Rochan Sinha, who's the co-founder and CTO at Newtrace, please.
My name is Rochan Sinha. I'm the co-founder and CTO of Newtrace. Today I'm going to talk about our work on development of next generation electrodes for alkaline electrolyzers and how we can improve the efficiency and flexibility of alkaline electrolyzers with this technology. Before that, I just wanted to talk about Newtrace, who we are, what have we been doing. Newtrace was started back in 2021 with the goal to help fight climate change by decarbonizing the industry. And for this, we have been working on various parts of the green hydrogen ecosystem. We are working on the electrolyzer systems, but also the components in order to improve the efficiency while reducing the cost of the overall system. And for this, we are doing development across the entire value chain, from electrocatalysts to the stack engineering and manufacturing, as well as to the entire system manufacturing. And for this, we're one of the first startups, or I think the only startup in India to have won the PLI bid for electrolyzer manufacturing. We are backed by leading investors, including Peak 15, Speciale, and other deep tech investors. In the last 5 years, we have worked on developing our expertise across various parts of the green hydrogen value chain. From the electrolyzer stack design and manufacturing, to the development of electrocatalysts and scale up of the production, as well as the balance of plant design and engineering. So in the last, I just wanted to briefly talk about our journey. We started off in December 2021 with the first membraneless electrolyzer in India, and actually I think one of the first in the world. We quickly scaled it up to a kilowatt scale system by next year. And in the next coming years, in April 2023 and December 2023, we were able to deploy a 10 kilowatt membraneless electrolyzer stack with a 100 kilowatt balance of plant, which was deployed at the BPCL R&D site in Noida. We went on to also deploy another site at ONGC with our partners HEB based in Trichy. And since then, we have scaled up to high temperature, high pressure systems, which can go up to 100 kilowatt in terms of the stack size. We are also now working on smaller scale systems. We have deployed one at BPCL for hydrogen for use in as a fuel in stove. So why are we doing this? In India, most electrolyzers are currently imported. We know which country this is imported from. Others are locally assembled with imported parts. So you will get let's say, the bipolar plates, the membranes, the catalysts or the electrodes, and we'll put it together in our country. So there are various parts with different levels of criticality in terms of how critical they are for the performance and the safety of the electrolyzer stack. For us, we are focusing right now on indigenously developing the catalyst coated electrodes, which is the most critical part in terms of both efficiency and performance, as well as the final levelized cost of hydrogen. We are also working on other parts such as the bipolar plate, which is another critical component, which is extremely relevant for our performance of the stack as well as the safety. So, in the last 5 years, we have worked on developing over 1,000 different combinations of catalyst materials and substrates in order to find the best performing catalyst materials, and we call these voltage. These catalyst materials have a low energy consumption at the stack level of around 43 kilowatt hour per kg of hydrogen produced. It can go up to high current densities above and beyond 0.5 amps per centimeter square. We have also been able to demonstrate stability of continuous running for over 1,000 hours tested, and cumulatively more than 5,000 hours. And the overall levelized cost of hydrogen because of this improvement in efficiency is close to 20% reduction in operational costs. And this is a fully 100% local value addition component. So everything from the electrode material to the catalyst material, everything is sourced locally. And we basically build the entire electrocatalyst up in our tech center in Bangalore. Finally, which is very critical for getting the costs down, is that we have a fully PGM-free design. So we are able to achieve such high efficiencies without the use of any platinum, iridium, or any other platinum group metals. We have been able to go not only at the lab scale. So what I'm showing you is not something that we have only demonstrated at lab scale. We have capacities to develop it up to 10,000 centimeters square in our current facility in Bangalore. We are also working on developing up to 25,000 centimeters square over the next year. Because we have done development on all parts of the green hydrogen ecosystem, we are not only able to manufacture the electrodes, but also assemble it in a stack that we developed ourselves in order to go up to higher current densities, and also do live factory acceptance testing, which is where we did the 1,000-hour continuous running of these electrodes. This is the final slide. I think this is a little bit complicated, so I'll go through it step by step. So what you're seeing here is basically what you see. No, it's not showing. Where? Yeah. Okay, anyway, no problem. So what you see there on the slide is basically a graph of voltage versus current, which means how much voltage do you need to drive a certain amount of current. The amount of current you drive is what drives the amount of hydrogen produced. So the higher the current you can drive, the higher the amount of hydrogen you will produce, but also the more amount of power you will require, because the voltage will also be higher. So the first curve that you see here on the top, the gray curve, is what a bare electrode, bare nickel mesh, is the level of voltage that you get. So you get around 53 kilowatt hour per kg of efficiency at a current density of 0.3 amps per centimeter square. With our voltage and electrode, with only the cathode and keeping anode as a nickel mesh, we are able to achieve 44.4 kilowatt hour per kg. And with including both anode and cathode, since we have developed both materials for the stack, we are able to achieve around 43 kilowatt hour per kg at 0.3 amp per centimeter square. And at 1 amp per centimeter square, we are at 48 kilowatt hour per kg, which is actually lower than what the legacy systems achieve at 0.3 amp per centimeter square. So what does this mean in terms of efficiency and overall improvement in cost? So, like I said, the efficiency gains of Voltagen is around 9.5 kilowatt hour per kg improvement over bare nickel systems. Let's assume a price of electricity of around rupees 6 per kilowatt hour, which is what you would get if you would connect directly to source. You will get an overall savings of around 60 rupees per kg in the overall cost of hydrogen produced, which is 20% of the overall cost at nominal loads. This sounds small, but this is a big improvement in terms of the efficiency for alkaline systems. Yeah, and this is, thank you for your time.
Thanks very much, Rochan. And I've seen Rochan over the last 3 years. When I first visited their facility in 2023 April, and quite impressive. You are putting India on the global map. Next, we have another global company. If you can have a round of applause for Nishesh Garg, who's the technology manager at Honeywell UOP.
Good afternoon, everyone. My name is Nishesh Garg. I'm technology manager at Honeywell UOP. Today, my presentation will be on LOHC, that is liquid organic hydrogen carrier, as ready to deploy solution for hydrogen transportation. My presentation does contain some forward-looking statements, so this is a standard disclaimer. The agenda for my presentation will broadly cover why, how, what, and when of hydrogen transportation and LOHC. So we do all understand why hydrogen is required to be transported. It is essentially because of a demand supply gap that is present there due to different levels of access to readily available and affordable renewable energy across different geographies. So how do we transport hydrogen? There are various options to transport hydrogen as on today, as you can see on my screen. If we start from right to left, the very first option that comes to mind is liquefied hydrogen. Now, liquefied hydrogen has first advantage is it doesn't require any carrier. It provides high density, high purity hydrogen at the point of import. But with liquefied hydrogen does come certain risk of leaks and explosions. The hydrogen compression process that is associated with this does require considerable energy, and it does require specialized insulated vessels, which leads to high capex. Next is the ammonia. Now, ammonia has its own established economy, which makes it readily available as a carrier for hydrogen transportation. It does have a high energy density and can be fired directly as a fuel, which makes it an attractive option. But if we delve into the details of it, handling ammonia does also pose some safety challenges. And even if those safety challenges are overcome, there are certain inefficiencies in the process that is required at the point of import. There does exist challenges and regarding the full commercialization at scale of the backrocking process to recover back the hydrogen. So unless ammonia is required as such as a product, it makes sense to look at other options. There comes in the LOHC, that is liquid organic hydrogen carriers. It locks in hydrogen in another molecule or a chemical and introduces the possibility to transport this hydrogen as liquid at ambient temperature and pressures. It enables the reuse of existing underutilized oil and gas resources and infrastructure, while it produces the high purity hydrogen at the point of import because of very high efficiency of the reconversion reactions. It is less dense, it is lesser in energy density, but it is very safe to handle it, while we use the same precautions that are used for the gasoline and diesel transportation and carriage. So in the last, the final column on this table, if you'll see what makes Honeywell LOHC different. Well, it is the only solution that is ready today at large scale and is based on a very widely traded carrier which has a large market. It introduces the possibility to retrofit existing assets, that is the old reforming assets in Europe, in Japan, and globally other places. This makes it an attractive option to make the unused assets work a bit harder. So, what is the LOHC solution and how it works? Well, it's a cyclic process where the objective is to transport hydrogen from a low cost to high cost hydrogen generation region. It starts with a carrier, that is toluene. This toluene or the carrier captures or locks in hydrogen through UOP toluene hydrogenation process, becomes MCH, and this MCH is then further transported to the point of import through the modes of import for gasoline or diesel. Now at the point of import, this MCH is treated through the UOP MCH dehydrogenation process, where the MCH converts back to toluene while it releases high purity hydrogen. And this high purity hydrogen is now available to be utilized for various industrial usages. And the toluene is again shipped back for the next cycle. Let me talk a little more about these processes. Now, toluene hydrogenation process is an extension of our existing aromatic hydrogenation technologies. The catalyst and the processes are customized to achieve more than 99.9% conversion, achieving or delivering 99% selectivity. The flow scheme is optimized so that there are minimal hydrogen losses. It is heat integrated so that the lower cash cost of production of hydrogen is achieved. Today we have more than 45 plus commercial references on similar technology for the benzene and aromatic processing. On the other side, that is on the point of dehydrogenation, MCH dehydrogenation process is an extension of UOP's commercial proven naphtha dehydrogenation technology, that is UOP platforming process. The catalyst is specifically modified for MCH, achieving more than 99% selectivity and conversion. There is a significant opportunity to monetize the old or shut down reforming units into this MCH dehydrogenation unit. We have more than 1,000 commercial references of platforming that is based on the similar technology. Let's dive a bit deeper and let's talk about how these technologies compare with each other based on the current commercialized technologies. Now, on the both sides, that is the hydrogenation and dehydrogenation processes, you will see we compare various operating parameters like the conversion, selectivity, temperature, operating temperature and pressure, space velocity. Both UOP dehydrogenation and hydrogenation processes are identical to existing and commercialized HV unibond and platforming. Now, this minimizes the project risk in terms of scale-up, startup, and the first product. Our solutions, our processes are backed by process guarantees and equipment warranties. Now, let me delve a little bit deeper in the terms of TRL, that is the technology readiness level. On the left side of the slide, you will see a simple stage-wise concept of TRL from 1 to 9, where TRL 1, 9 implies basic concept, while the TRL 9 implies commercial operating unit. And on the right side, you will see the comparison on technology parameters of both of these processes, that is the unit configuration, operating and conditions, procedures, equipment package, and equipment selection as well. Both hydro and dehydro processes, TRLs, are identical to HV unibond and platforming, hence at TRL 9. Since the feed, that is the carrier, is new, they are extensively tested in our pilot plants, both in US, Chicago, and here in India, in Gurgaon, which makes it at TRL 6. UOP is a single licensor that is ready today to offer full supply package for the UOP LOSC solution for hydrogen transportation. You can say that because of our experience in these process technologies, while others are at mini demo units, we are at 60 years ahead of the curve. So UOP as a single licensor is ready to offer full-scale supply package, leading to project financing and risk mitigation, commissioning, and other benefits. Now let me close my presentation with a case study of a comparison of LOSC versus ammonia. The case that I have chosen here is hydrogen produced from India and transported to Rotterdam, that is a port in Europe. 50 kT of hydrogen from electrolysis produced in India. The ammonia data for this comparison is taken from SNP tool, while the LOSC data comes from our Honeywell LOSC solution. Now, if you see this flow diagram closely, it compares two technologies on the terms of delivery of hydrogen and the various components in the whole value chain. Here you see on the left side, that is ammonia if you talk, the 50 kTA hydrogen produced from electrolyzers become 260 kT of ammonia with 46.7 kT of hydrogen in it. It requires 5 ships of largest size for ammonia service available. Now, this ammonia, when shipped back to point of import and cracked, it finally delivers 33.8 kT of hydrogen. On the other side, if you see the LOSC solution, this 50 kT of hydrogen becomes 830 kT of MCH, which contains 49.9 kT of 2 of hydrogen. It also requires only 5 small general purpose handy size tankers, which are available in multiple of hundreds today. This carrier on dehydrogenation on the point of import delivers 49.87 kT of hydrogen, which makes the final produced or delivered hydrogen much more than the other side. Capex wise, if you focus or compare the major capex for the coming from the hydrogen generation and RE generation, which we understand that is the solar panels and electrolyzers. But if we compare hydrogen transportation closely, both LOSC units comes at less than 70% of only the ammonia synthesis of the same scale. For the same case, if we go further and compare and see how hydrogen transportation compares on dollar per kg hydrogen transported terms. Now these bars include conversion, storage, shipping and reconversion. It covers various aspects of transportation, that is by pipelines, trucks and ships. Since we are talking about long distance hydrogen transportation, ships make sense. It's very much evident that LOHC becomes very competitive, rather lower price of final delivery than ammonia in this case. I'll conclude with the final remarks about the when of LOHC. So it is happening today. LOHC is ready solution for the producers and the importers of hydrogen that are interested to work in the hydrogen transportation value chain. We are working with INEOS for world's first commercial scale LOSC project at multiple sites in the globe. Thank you. We are present in Hall 3 and I welcome and invite you to visit us. If there are any questions, please connect with me after this or on LinkedIn. Thank you.
Thank you very much, Nishesh. That was a masterclass that you've taken for all of us here. Next, can I invite Mr. Shrikant Mishra from Technip or Relay? A round of applause for Shrikant, please. Thank you.
A very good afternoon to all the people present here. I am Shrikant Mishra and I am from Technip Energies. And today on this stage, I am representing Relay. Relay is a joint venture company between Technip Energies and John Cockrell. So before I start, I would like to thank my fellow speakers to set up the tone for this session and bringing out all the aspects of hydrogen, or I would say green hydrogen. So before I start, the most common term that we have heard today is intermittency by our fellow speakers. And in the next 10 minutes during my session, I will be taking you through the opportunities and the options that are available to overcome this hurdle with respect to intermittency. E-methanol or synthetic methanol, as we know, has the potential to carve the path for decarbonization, especially for the hard to wait sectors. If we see, the traditional methanol production was by the fossil fuel route, but the synthetic methanol that is produced by capturing CO2 from the flue gases, hydrogen produced by renewable energy termed as green hydrogen. And together it has the ability to reduce the CO2 emissions, as it is a closed carbon loop wherein upon usage of e-methanol as a fuel, the CO2 emitted would be equivalent to the CO2 consumed or extracted from fuel gases. So it's a carbon neutral path. It also will improve our reliance on fossil fuels. It will decrease the reliance. So, and if you see the Indian current scenario, there is a lot of projects and lot of investment coming on renewable energy. So the power to X or power to green chemicals combined with the renewable energy sector is becoming the tool for decarbonization. We as Rely are supporting the whole value chain by increasing the affordability, by improving the cost and the efficiency. With the expertise engineering from our team, with our electrolyzer design, with our BOP optimized to the best maximum extent possible, we are coming with an end-to-end solution wherein right from the generation of the hydrogen molecule up to the optimization studies and at the end the support required for operation and maintenance of the electrolyzers, we are there at every stage to support the whole value chain. Whenever we see a new technology coming up, it is always associated with its own share of challenges. Green hydrogen is no new. It is also coming up with its own share of challenges. If we could figure out the four important pillars where these challenges are basically concentrated upon to, we would put them into four baskets, starting from the technology. Like my speakers have already emphasized that technological maturity is a challenge. And the way to move forward is to basically bring out the pieces of mature information from other sectors or other technologies and try to merge them together to bring out a holistic, more mature technology. The markets, the markets, if you see, are very volatile. It is high time that there is an integrated market that is there, which takes care of the feedstock issues, which takes care of product issues, which takes care of the consumers, the offtakes. So basically integrating the whole sector so that we can have a long-term solution or a long-term contract, because revenue is always important for sustaining a growth and also for bringing up new investments. So this market, when globalized and integrated, can be a key improvement. Regulations. If you see, as on date, the definition of green, it changes from country to country, and this is one of the challenges in the sector. Bringing all of these definitions on a single platform will surely help in growth of this sector. The favorite word, intermittency. Intermittency of renewable energy can be overcome if we have a design margin, if we can avoid the the requirements of having a very high capex on the renewable energy factor, by having an optimized plant which is flexible enough with suitable standby. So these things can help to evolve these challenges. Now, as Relay, what we always promote is that we should have an early engagement, because we believe that that is the best place where we can support the whole study, support the whole integration to have the best solution, to take care of the opportunities, to take care of the limitations and convert them to the best possible option. As an organization, we help in defining the system architecture, we help in integrating this whole system, giving an optimized solution, and also look into the aspect as to the investment strategy, the export strategy, and so on. With ODC, which is a powerful dynamic tool, we have the capability to integrate the power, the fluid, the consumers, the integrators, the converters, and finally the storage system. So all these integrated together on a common platform help us to give the most optimum solution. So to take towards the stages of a solution finding, I would present a case study wherein we were given a challenge to produce a certain amount of e-methanol with the best LCOM possible without compromising on the average production. So with that challenge, we have defined the network or the schematic in our software ODC. If you see the scheme, the yellow parameters are the fixed parameters, whereas the blue ones are the variable parameters. So at the start, we have taken a 600 tons per day methanol capacity, which was the capacity of the plant from the client, and then we have run this requirement on our software ODC. Now ODC has the capability to automatically define the algorithms and define multiple operating scenarios. So each blue dot you see is basically an operating scenario. Now here if you see, there is a black curve at the top which is called the Pareto curve, which is basically the point where at that particular levelized cost of methanol, the best production or the maximum production is achieved. So, so this was the conventional case. When we see the results of this conventional case, we see that around 600 megawatt of wind farms are there. You see hydrogen storage is there around 691 tons with the electrolyzer capacity of 375 megawatt. Now with this configuration, we are getting an average production of 570 tons per day methanol. So the next step was, can we bring down the LCOM less? So with that approach, we have added two main things to the design. First, the flexibility, which means that the plant can operate at lower capacities. That is done by providing engineering solutions to the plant, to the design. Secondly, by allowing stages where the renewable energy production is very less, so we'll run only the bare minimum facilities, but at the same time keep the plant in standby mode. So this is helping to optimize the renewable energy capex or the or the installation. Now, if you see the first black Pareto curve is flat, which means that there is very minimal change in the LCOM with the cost, with the average production cost. But if you see the yellow curve, that is more of steep, giving us the option to select for the same LCOM multiple average productions. Now this gives us the option to select more. And just for info, like ODC doesn't give you the final point, it gives you multiple points based on the client requirement, based on the market dynamics, based on the capex investment strategy, client requirement, your consumer strategy. You can select a suitable point that suits your requirement best. So if we see, when we tabulate the results with the flexible case, we see that there is reduction in the capacity of wind installation, in the capacity of electrolyzer installation. Hydrogen storage sees a significant reduction, but at the same time, what we see is that the average production has come down. So there's a compromise. So the next step, we thought, let's have another alternative wherein we are keeping the LCOM minimum, but at the same time we are improvising or improving upon the average production. So with this intent, we have changed the approach. Rather than fixing the plant capacity, we have fixed the wind capacity or the wind installation capacity to 600 megawatt. Now with this result, we have run the simulation again, and I would like to take through all the four curves. The extreme right curve is the Pareto curve for the conventional case with a fixed methanol plant capacity. The second black curve is for the conventional case using a variable methanol plant capacity and a fixed wind farm capacity. The first yellow curve, which is towards the bottom, is a flexible design wherein we have kept the plant capacity as constant of 600 metric tons per day. Whereas the extreme left Pareto curve in yellow is the point wherein we have fixed the wind capacity but kept the plant capacity variable. Now if you see, for the same LCM or almost same LCOM, we are able to increase the average production by almost 30%. Now this is where the benefit of these optimization tools come into. Without compromising on the LCM, we are able to achieve a higher average plant capacity or production capacity. So if we see the results after this further modification or further optimization, we see that we have crossed the hurdle and are achieving almost 590 tons per day of methanol. But with that, we have also increased the methanol synthesis capacity. So, but with this, we are not compromising on the levelized cost of methanol. So all these factors put together, if we sum up, what we see that for first option, the conventional plant, the wind installation, electrolyzer installation was significant. The average was 100% for the LCOH or LCOM. But when we do the design as flexible, we add flexibility. we improve on the LCOM or LCOH, but at the same time we compromise on the on the on the average production. At the third stage, when we try to come up with the solution wherein we increase the capacity of the production, we see that the average production of methanol has increased. So if you see, a design has to be flexible so that it can reach the best solutions. It needs to identify the constraints and convert them into strength. There should be a strategy to build upon the plant to see the investment plan. So the key takeaways that I would like to propose as a part of my session or as a part of my presentation is that we as Relay understand the challenges and the context of the green hydrogen power to X business. We have the expertise to convert or to back the whole business, and this is a continuous feedback process where we are always learning from our experiences, from our past projects, from various clients. So every interaction is a new learning. We also offer the most informed and expert techno-economic studies by virtue of our software, by virtue of our team, by virtue of the powerful tool called Odyssey to define the best plant configuration so that the capex, the opex, and the path forward for a sustainable green hydrogen can be achieved. I thank you everyone for your time. Thank you.
Thank you, Shrikant. And also to add to this, Relay and Technip, you are one of the few solution providers involved in the highest number of projects in India. And, and I think that is a testament to the work and products and services you offer. So with that, can I welcome Mr. Vipul Bansal from Coal India Limited. A round of applause for him, please. Thank you.
Good afternoon to everyone. Let me thank all of you. It's my honor and privilege to present a technical paper at IEW 2026. So, I'm the co-author of a technical paper named From Sun to Shaft, Powering Mines with Hydrogen. And my co-authors are Shri Rajiv Datta sir, General Manager E&M Coal India Limited, along with Shri Alok Jha sir, Senior Manager Excavation. So, as I am from Coal India, let me ask you one thing. From Coal India, what comes first in your mind? Either it would be black or grey, but not the green. But today, on the contrary, I am going to talk about green. As there are certain challenges of Coal India Limited. As Coal India is world largest coal producing company of the world. But in my technical paper, I am going to refer two problem statement of Coal India. First, it would be not the digging of coal, but it's actually driving of coal. And second would be the power evacuation of solar power plant installed at Coal India Limited. I'm going to talk about both the problem statement in the forward slides. As the objective of technical paper is to resolve these two issues, as I'm going to tell you that more than 4 lakh kiloliter of diesel we consume annually, and 60 to 70% of diesel are consumed by the dumpers and trucks, which are being used for the moving of coal from mines to the nearby coal handling plant. And it's if we talk about in practical way, it's like filling 160 Olympic size full size swimming pool with such diesel. And as we know, we are not the oil our country is not a oil surplus country. We actually import the oil from the other countries, so we rely on the other countries for that purpose as well. Second would be the government of India, Ministry of Coal, has given the target to set up over 9.5 gigawatt of solar power plant capacity at the abundant mine and the area held by the Coal India. And as we know, all the coal mines are situated at the remote places of Jharkhand, Chhattisgarh, Odisha, West Bengal, and UP. So there is not the certain infrastructure which is required to evacuate such a huge amount of the power. And if we have such infrastructure, but there is a very technical and commercial issues with the open access, net metering, etc. We have to deal with the utility. but there are certain challenges to do so. So as I talk about, there is this graph I am showing you, which depicts the increasing trend of diesel consumption in coal India, and more than 4 lakh kiloliter of diesel is being used annually by CIL, and 70% of the diesel is used in driving the dumpers and trucks. So here comes the innovative part, which I talked about. I'm going to talk about green. We want to set up a green hydrogen power project in CIL, and using renewable energy which comes from the solar power plant, which is a best integration and innovative solution for Coal India Limited. By referring this paper, we'll solve both the problem statement as I mentioned below. In solving this problem statement, we are going to use PEM based electrolyzer, as we all from the hydrogen based background, everyone knows this. There's a electrolyzer which produces hydrogen with more than 99% purification, and it splits the water molecule to hydrogen and oxygen separately. And the power requirement we'll get from the solar power plants, nearby solar power plants. And for water, as we know, when there's a coal production is being exhausted in any mine, so there would be the generation of mine voids filled with the waters and make of water and rainwater. So we are going to use that water for the purpose of hydrogen plant. For this purpose, we require the more advancement in technology of hydrogen mobility in India. We are fortunate that Government of India launched National Green Hydrogen Mission in 2023 with around over 19,000 crore rupees, and most of the reputed company IRCL, NTPC Green, along with Tata and Ashok Leyland, have done immense work in the green hydrogen mobility work. They have installed e-rickshaws, dumpers. They have buses also on trial run basis. Tata Motors and Ashok Leyland and Reliance Industries are working on the pilot project for hydrogen-driven vehicles. In continuation of Tata Motors, NTPC Green and Indian Oil have also made a joint venture for movement of buses at Ladakh. All of these are on trial run basis, but they are in a very advanced stage. So we will use hydrogen-driven dumpers or trucks of around 28 to 30 ton capacity for the driving of coal, for evacuation of coal in a coal mine. So whatever I have talked about, it's not a thesis and a concept, but we have considered a case study as well, a actual project, what it would be like. So this is the concept that we are going to install around 55 to 55 megawatt AC solar power plant at a abundant mine of Coal India. Land of around 123 hectares is already under leasehold of Coal India Limited. We'll use the water, and we'll set up a hydrogen power plant nearby, hydrogen plant, and that could produced hydrogen we shall use for the fueling dumpers, and subsequently we shall reduce SOx and NOx pollutions thereby. So case studies of Jamuna and Kotma area of southeastern coalfields, one of the largest coal producing company of Coal India Limited. We have surplus 123 hectares of abundant reclaimed land at which mining activities have been exhausted. At 123 hectares, we shall install 55 megawatt AC or 77 megawatt DC solar power plant. And the power consumption of that area is not immense and huge. So surplus energy we are going to use for hydrogen production. This is the longitude and latitude of the exact area, whatever I am showing you on the slide. So assuming on the conservative side, apparently in Chhattisgarh, Jharkhand, Odisha, we get around 5 to 5.5 units per kilowatt hour per day generation. But I am assuming only 4 kilowatt hour, 4 units per kilowatt per day, and we will get around 803 lakhs units annually on the conservative side. By these units, we can set up a 10 megawatt capacity of green hydrogen plant using PEM technology. which will produce in turn around 4.3 ton hydrogen per day. And from this huge hydrogen production, we can use in around 39 number of dumpers of around 28 to 30 tons. 28 to 30 tons have been considered because they are recently launched by the Tata and Ashok Leyland for trial run. This 10 megawatt hydrogen plant shall produce 4,313 kg of hydrogen per day, which shall subsequently fuel around 39 tons of dumpers. So this is the actual figures of that Jamuna Kotma area, Amadand mine. We are using as of now, we are using 62 numbers of trucks for coal evacuation of 30 ton and 150 numbers of trucks for overburden. Overburden implies with the sand which is situated above the coal. So we are using 150 numbers of trucks of 20 ton for evacuation of overburden and for rehandling of overburden. So using these 39 tons of, we shall replace these 62 numbers of trucks which are using for coal evacuation. Around 50 to 60% we can replace using these hydrogen trucks. So there comes the investment part. Actually, this is concept. I am showing the concept along with the financial viability of the project as well. For solar power plant installation of 55 megawatt, we shall be using around 336 crores of capex of CIL, and for maintenance of the solar power plant, as per the norms, we have considered 5.75 lakhs per megawatt, which is around 3.85% of the capex. For 10 megawatt hydrogen, for setting up the 10 megawatt of hydrogen power plant, we have assumed 231 crores rupees, and this is on the conservative side as well. As we know, there is a huge advancement and technology enhancement in hydrogen power, in green hydrogen projects, and in electrolyzer there is the advancement of the technology. We have considered this figure for the same capacity of green hydrogen project installed at Guna by GAIL India Limited. So this 231 crores shall reduce definitely, but I have considered the same. So this is the total investment of the project would be, and we have prepared a conceptual note as well. For setting up the 55 megawatt solar power plant on our own land shall be around 336 crores. Land is already under the leasehold of Coal India. For setting up 10 megawatt of hydrogen power plant, we shall be requiring 231 crores. And I have considered not the outsourcing or partial hiring option. We have considered, we are considering to own the 39 number of trucks. So assuming 13.65 crores rupees for one truck, total project cost would be around 580 crores. It should be actual figure. So there is a certain rule by Ministry of Coal and Coal India Limited which are being followed, that any project for that internal rate of return is about 12%, that project would be viable. But consuming the cash flow and discounted rate, we have calculated IRR as well for this project. That should be around 8.24%, which is not more than 12%, but which is not at par, that below as well. And these figures are on the higher side. With the advancement of technology, this may be on lower side as well. But there comes the more interesting part. In today's world, for production of hydrogen, we are also getting carbon credits as well from Government of India. So interesting part is we shall save around 10.25 million liters per year diesel by only deploying 39 number of trucks driven by hydrogen, and it's similar to the fleet of 6,000 cars, removing the 6,000 cars on the roads of India. It's that big, it's that impactful. So as we know, burning of 1 liter diesel emits around 2.68 kg of CO2. and we shall save over 27,000 kgs, 27,000 tons per year CO2 emission shall be restricted by implementing these projects. Subsequently, we shall reduce SOx, NOx, PM, particulate matter pollution as well, and this will inherently save the life of the mine workers. It will make the better place to work in the mine. So, consuming that carbon credit as well, higher forecast around 11.44 crores per year shall be possible. So there are certain takeaways, and one thing I would like to mention, it is worth mentioning that this is a example of only one mine and one area. We have surplus land, we have surplus of, we are using over 25,000 of dumpers in Coal India driven by diesel, and the most interesting part is this idea is scalable and there shall be no hurdles as well. So key takeaways is whatever solar plant we have already installed, Coal India has already installed more than 3 gigawatt of solar plant capacity in India. So power evacuation issue shall be resolved using this. We shall save more than 10.25 million liter diesel per year. Fuel security shall be ensured by this. More than 27,000 tons of CO2 emission shall be restricted, as I told you, equal to the removing fleet of 6,000 cars on the roads of India. Air quality, which is a bigger issue nowadays, shall be fighted along with this, and it also aligns the government national green hydrogen mission net zero commitment, and it will make India self-reliance and long-term sustainability shall be there. And most interesting part is that the idea is scalable, and it's under the consideration of Coal India and government ministry. So from sun to shaft, we are transforming coal mining with the clean hydrogen. With these words, I'm wishing you all happy and sustainable future. Thank you so much.
Next, if I can invite Dr. Satabdy Jena. Ma'am, a round of applause for ma'am, please.
Thank you for the introduction, Nishaanth. Good afternoon, everyone. I would like to present our work, which is also a part of industry and academic collaboration, on the reliable operation of green hydrogen electrolyzers using grid-forming inverter technology for constrained weak grid infrastructure. Before we dive in, please do not base your investment decisions on what I speak today. Next. So, the process of electrolysis, when aided with renewable electricity, is often termed as green. The standard being less than 2 kg of carbon dioxide equivalent per 1 kg of hydrogen produced. Now, Shell also produces electrolytic hydrogen. We have a 200 megawatt facility at the port of Rotterdam, and we have 10 megawatt proton exchange membrane electrolyzer at the Rhineland refinery, operational since 2021. And there's a planned expansion of 100 megawatt by 2027. Now, the hydrogen usage globally is also estimated to increase manifold, approximately 3 times its present usage as per IEA. And as we speak, the rollout of hydrogen electrolyzers, which are large scale, are also going to impose a big problem on the power grid. Let us see how. Taking a look at the picture as shown on the slide, we see that the grid, along with a higher penetration of renewable sources, feeds power to the electrolyzer via a power electronics device, which converts the AC power to DC for the interconnection of the electrolyzer, and the end product hydrogen is used up for hard to decarbonize industries like steel, cement, fertilizers, etc., and in gas networks for hydrogen blending. Now we do see that there are a lot many red flags in this entire system, because these are complex energy systems and they interact with each other. What are they? Let us go explore. So the challenges of hydrogen electrolyzer integration are that we do not want the presence of harmonics. We do not want ripples either at the DC voltage link to where our electrolyzer is connected. We also want an electrolyzer which has a very fast response, And we also want it to be controlled and have a possibility of riding through the power grid faults. So what is the solution? For the high power rectifiers, which we have actually seen the numbers from our previous presenters on a megawatt scale, the solution conventionally has been to use thyristors. But now we are moving towards enabling transistors for being used in modern power electronic devices, which are also called voltage source converters, and that solves few of the problems like harmonics, ripples, etc. And for obtaining a fast response, we have analyzed in literature that the proton exchange membrane has a very fast response, and it has low crossover hydrogen, and it has very lower start-stop degradation, and that's why we have included it in the scope of our investigation. Next, we have actually overestimated the power of the grid and its capability, because the IPRs that are connected, the inverter-based resources that are connected to the present power grid, has been connected with an idea or with an assumption that the grid we are looking at is already strong. But with the more and more penetration of renewable energy sources, this will not be the scenario for the future power grid. We are losing, or we are retiring thermals, and we are losing most of its inherent inertia or stability, and hence we need a factor to measure the grid stiffness. How do we measure it? Let me introduce the term known as short circuit ratio, in which if we have a higher short circuit ratio, it denotes a very strong grid. If we have a very low short circuit ratio, it denotes a weak grid or representative of grid which has a lot of renewables penetrated. Now, it has been identified that in order to deal with the low short circuit ratio of the grid, basically grid forming inverter technology helps. How it does, we will see in the next slide. But before that, the solution would be not only to have an hydrogen electrolyzer in place, but also to have a coordinated control that looks after this complex energy system. Now, as we move on, a word of caution that the short circuit ratio just indicates a quick strength of the grid and does not include multiple control system interactions that might take place because of the multiple inverter integrations that we are putting onto the grid. Now, in this figure, as you see, the power supply to the electrolyzer is being pumped through a modern power electronic device, and the green box that you see is an impedance. So this impedance decides whether the grid is going to be strong or weak. So higher the impedance, the weaker the grid, and lower the impedance, the stronger the grid. And this is how we model that scenario of having high renewable penetration. In order for an electrolyzer to have a more commercial likeness, we have taken up from the Bloom Energy data sheet, and we assume a 1 megawatt electrolyzer connected at the point of interconnection, utilizing 800 volt DC. Now, we would be testing with this model two modes, strong grid operation and weak grid operation. But before I move on to the next slide, would like to present one term which is known as phase lock loop. So it helps the inverter to lock on to the grid frequency so that we are synchronized and we are not disturbing the stability of the system. It is quite analogous to how we run on a treadmill. So this slide seems to be busy, but I will take you through the graphs. The first one is a strong grid mode of operation in which the desired voltage of 800 volt DC is tracked and the desired power demand is being met through the grid. All is well. But the next stage in mode 2, we see that the PLL that I just introduced is not able to track the frequency of the grid because of the weak grid scenario, or let's say because of high renewable penetration. Because of which we see the control system malfunctions and the power drops, quite analogous to how the person falls on the treadmill. Next, with the problem statement in hand, we move forward of designing the solution. So we tried to interconnect a grid forming inverter with BESS technology at the point of interconnection where the electrolyzer is also connected to the grid. We also see there are two boxes in red, B1 and B2, which allows for the quick connection and disconnection of the grid forming inverter and the electrolyzer respectively. On the right hand side, you will see that there's a crisp representation of the control system for grid forming inverter technology, which tries to dictate the voltage and the frequency at the point of interconnection. So the mode of operation tested with these are, before I move on explaining the slide, so realizing that there will be a need for grid forming inverter technology, Grid India has recently developed a white paper released on December 2025 on grid forming inverter technology and its applications in the Indian power system. So moving on to the results, we see that in the first scenario, the grid forming inverter acts as a voltage support. Now it injects only that much amount of power which was required to maintain a stable voltage at the point of interconnection, and the rest of the power is drawn from the grid by the electrolyzer. Next, we move on to the power support mode, in which we slowly increase the reference command to the grid forming inverter, and eventually the entire demand at the electrolyzer is being met by the grid forming inverter, but we have not yet disconnected the grid. Now moving on from the second level to sub-second level, we have tried to demonstrate how the grid currents would look like at the point of interconnection on a lab test bench. They are unstable, as you can see from the first graph, because of the weak grid scenario, and then they get stabilized because of the addition of the grid forming inverter technology. There is also one more situation we have taken into consideration, which calls for standalone mode of operation. So there might be a scenario where the voltage frequency and voltage excursions take place well beyond the prescribed limits, and hence as a result the protection switchgear trips and our power grid is disconnected. In that scenario, the entire power demand is met by the BESS GFM, and we have a smooth operation and thereby reducing the downtime. So we'd like to say that the results so far have demonstrated that when we speak of integration of electrolyzers to the grid of the future, which is heavily renewable dominated, grid forming technology helps to improve the system performance, reduces the downtime, and also is able to provide a standalone operation. Further, we can also see that we are able to ride through grid frequency events. Thus, it is the grid code requirements are met by the complex energy system, which varies from country to country. However, the challenges here in the study are that we have assumed a simple electrical equivalent of the PEM electrolyzer, and it calls for a detailed modeling in order to capture the chemical process taking place in the electrolyzer first, and then secondly, there has to be standards for examining the grid forming inverter for BESS. According to the reports released by Grid India, the low-hanging fruit is by tweaking the control formula for BESS and using it for such stabilizing operation. The same does not apply to PV and wind as per the document that is released. And we also need to take into consideration that the coordinated control of the grid forming inverter with the grid actually helps to interconnect both renewables and electrolyzer at the point of interconnection. So I made sure that all of us here take a little bit of electrical engineering with themselves when they go. And with this thought, thank you.
Thank you very much, Dr. Jena. Next, if I can welcome Mr. Sachin Chugh on stage. A round of applause for Sachin. Sachin is the energy and hydrogen lead at the global consultancy firm ARUP. Sachin, over to you.
Thanks, Nishaanth, for the opportunity, and thanks to the organizers. I very well appreciate and understand that I'm standing between all of you and lunch. We have been running on time, and I'll try to finish my presentation and my talk pretty quickly. I think on the panel we have had the fascinating discussion on the technology, on the intermittency, on utilization, on balancing. I think the last, one of the important legs, which is there, which could enable the success of the hydrogen economy, is all about regulatory. When we move from the space where we are able to produce hydrogen, it becomes very important that how the offtake of hydrogen has to be enabled. The captive consumption is one aspect to look at it, but when we start producing in massive volumes, it is going to be the ease of trade which can enable the development of the ecosystem and the scaling of the technologies. And that's where the work which we have been doing at ARUP, which is a global consultancy headquartered in London, and we have our strong presence in India, being the technical advisors to the government of UK on low carbon hydrogen. We have been able to assess from the regulatory as well as from the technical perspective that how we can enable the trade of hydrogen across the continents. And one of the important aspect in that particular front is the CO2 standard, which is being talked all across the world. Now, my slides are going to cover some information related to that, and we are seeing from the carbon lens the various aspects of hydrogen. I would not like to go into the details of the colors of hydrogen, but as all of us know that it is not a primary fuel. So we need some primary fuel to develop this secondary fuel, and we have been using natural gases of the world as well as naphthas to produce hydrogen in a conventional manner, which is one of the largest production methods in the current scenario. However, we have been seeing other aspects related to biomass, the electrolyzers, as well as with natural gas added with the carbon capture as some of the options. So we are also seeing pyrolysis, the methane splitting, getting the carbon as a metal as well as hydrogen as a gas as one of the prospective processes. Now the question for the regulatory bodies is that chemically whatever is being obtained from these processes is all going to be H2, and that is so the differentiation is not going to be there. However, the difference for enabling that kind of differentiation, some kind of tagging is required, and that tagging comes with the carbon intensity. Imagine this carbon intensity we can imagine as a part of the regulatory conditions which are going to influence how the hydrogen is being produced. Drawing a parallels from the cricket analogy, I think the bat and the ball and the wickets are going to stay the same, but each match is going to have its own excitement, and that excitement is largely dependent on the conditions of play. And that's where these conditions of play here in the hydrogen arena are related to the carbon intensity, the conditions in which the hydrogen is being produced. So it is the same molecule, but it is the radically different carbon stories which we need to address. And when we have to trade this, then it becomes equally important that how we are measuring this. And then when we are entering into the measurement zone, it becomes a game of variables, whether we are talking of the emission factors, we are talking of the methane leakages, the carbon capture boundaries, or the overall system boundaries. So this means that when we have to certify this particular molecule, it becomes a game of how we are fixing our boundaries, whether it is well to gate number in terms of managing the carbon intensity, or it is whether the methane leakages have been accounted in the system or not, whether the electricity which is being produced is matched with the production of hydrogen on time basis, and that time is whether an hour or a day or a month. It becomes very critical, and whether the biomasses of the world are being considered or not. So this means that technically hydrogen appearing to be very seductive, we all have understood that economically it is very stubborn, but this also means that regulatorily it is conditional, and those conditions are going to see that how we are able to cover that trade. So when we compare that the trade of oil and gas, or especially the crude oil as well as LNG, we find that oil has been trading for years, but the oil trade is happening in terms of quality. We have seen different indexes of the crude oil, while the natural gas trade is currently happening based on the energy content associated with the molecule. But when it comes to hydrogen, I think as of now the trade is only happening based on trust. So that quantification has to change, the narrative has to change, and therefore that trust has to give a way to a certain measurable number, and that number is the number of carbon dioxide intensity attached with the production. Now, this also means that these colors are not going to survive, because colors are not going to be the passport for hydrogen trade. We need some quantifiable numbers, and these numbers are going to have to be uniform across the world. If we are having different numbers, we are going to have the restrictions at the borders enabling those constraints, which probably in physical form, when we enter from one country to another. So when it comes to the measurement, we are seeing there are two mechanisms. One is some countries have adopted the well to gate studies, which means that yes, from the extraction of the raw material up to the production of the molecule, and that is a system boundary. And some of the countries have quoted well to wheel. This means that the end application is also being accounted, and the carbon measurement in order to enable that end application is also being accounted in the system. And therefore, the well to gate numbers, well to wheel numbers are going to be inherently different as far as, because the system boundaries are different. So what it is causing, we like on the screen, we have the numbers from various countries. The graphs are dancing up and down, and this means that we are not consistent. But when we try to translate it into how difficult it would cause the trade to happen, so we have captured some of the cases which are hypothetical cases. But when the exporter is, let us say, on the first bracket, it is UK, and it has to and it has to export it to European Union. Now, when these two standards are different in these two countries, because the mechanisms and the measurables are different, I think the risks associated with the downstream transport, because of the well-to-wheel consideration in European Union vis-a-vis the well-to-gate composition, measurement in UK. So those carbon intensity numbers, when they are going to be added, if the border of European Union has to be crossed, I think they are going to change the equation for that particular trade. It may happen that once the hydrogen which is qualifying as low carbon hydrogen in UK might not be qualifying as the so-called low carbon hydrogen in the European Union. And this means that there can be a boundary mismatch, there can be a false competitiveness risk, there can be a numerical parity but regulatory conflict depending upon the laws of the land. There could be a structural export parity. So these risks are going to inhibit the free trade across the world. And we are living in the world of trade agreements being bullied, being supported by various countries. So we can now very well appreciate that how important is the cross-continental trade. And so one question which is largely from the technical perspective, we can understand why global hydrogen standards vary. So these vary because of number of these reasons, because the current countries are having diverse energy mix. There are inconsistent carbon accounting methodologies, policy and regulatory differences are there, and there is no uniformity. Therefore, we need to have a global hydrogen standard, and that will enable the standardization and transparency. It should be pathway flexible, because each country should be choosing its own way in how to produce hydrogen, and regulatory alignment and cross-sector integration is must. So what we did was we devised a methodology for this harmonization. And this particular methodology is based on two aspects. Rather than making some hypothetical assumptions, what we did was that there are two major aspects of looking at it. One is how the energy mix of the countries or the leading countries is going to change going forward. What are their preferences in terms of adopting the renewables, or they want to stick to the fossils? And second one was, what is the preferred hydrogen production pathway which is being promoted by those companies? We then added another layer on the top of the how the political system and the overall performance of the country is in terms of the energy demand growth, or the policy score, or the GDP growth. All these factors are going to influence how hydrogen would be produced and which type of energy would be used. Then we ran our customized model to arrive at one number of which we feel that it should be in the form of a range rather than a fixed concrete number that would give a lot of flexibility for the world to configure and maneuver. So these are the two cases, which you are seeing on the screen. One is the resultant emission factor we calculated, which was based on the primary energy availability in the country, and with a lot of factorization, we did this kind of modeling. And the case two is what is the preferred or likely to be the preferred route for hydrogen production going forward based on the different policies and the discussions which are happening on those countries. So on the right side, this is the result of the simulation and the model. So what we were able to get was that contrastingly, we can find that the China and India are having very contrasting styles when it comes to the way in which they have projected the hydrogen productions going forward. Also, we see that the countries like Japan and other countries like Korea are very consistent in terms of whether they want to go for the primary energy model or they want to go for the hydrogen production, the kind of pathways which they have shortlisted for hydrogen production. So they are very akin to each other. And also the likes of UK and particularly India, how we are going to see the things that whether it is the primary energy or it is the energy based on hydrogen production coupled with CCUS, how the route is going to influence. So we topped it up with the country specific factors, which again, I indicated that it is China, India, Japan. All these are going to have different combinations of these variables, added the scores and the normalization factors on it to arrive at something which was very interesting. And this particular graph indicates the result of our modeling. On the left hand side, it is the number which you are seeing is about based on the hydrogen production, and on the right side it is based on the forecasted primary energy mix, which is the committed values for the various countries depending upon their net zero goals. And that's where we see this particular band of somewhere around 2.75 to 2.95 is roughly closing to 3 kgs of CO2 being permitted per kg of hydrogen. And to the contrast, this band is not varying very much from some of the stringent standards which the countries have set up. So it will give the flexibility to those countries, those who have set up the stringent standards, and it will give some kind of penalties to those countries, those who are not able to account and take the green aspects very seriously. So I think this range, which is very consistent, that is where we can adopt as a universal standard for hydrogen. So this means that this is a running number, not a very fixed number. It gives some kind of maneuverability to the countries to decide what form they need to go. And so these cases, they combine and take into account two of the basic scenarios based on which the energy policies are formulated. Hence, so it can enable the free trade, it can enable the scale up, it can enable the offtakes that is being perceived as one of the great hindrance at current modern times when the offtake is not assured. So it is impacting the developers not to not to go for the financial investments. So I'll just like to conclude here very quickly that hydrogen standard can be termed as a compass. It doesn't tell us when the ship has to sail, at what speed the ship has to sail. It only tells us in which direction the ship has to sail, so that all the if the ships are starting from the different shores, or all they can do is they can aim at that North Star where they combine and help the trade to happen. So so it is all about for the fluent conversation to happen, we don't need the common accent, I think, but what we need at the current state, particularly relevant for hydrogen, is a common grammar. And this particular hydrogen standard, or the harmonization of hydrogen standard, is a way in that particular direction. So I'll just pause here at the end of my talk. Thank you very much for your patient hearing.
We'll bring this to a close. I think this is the most diverse panel I've ever been a part of, but thanks to all of you all.